Hello, this is Unit 6, Lesson 13, Graphing the Standard Form Part 2 Notes. The learning objectives for this lesson is I will be able to explain how the b in y equals ax squared plus bx plus c affects the graph of the equation, and I will be able to match equations given the standard and factored form of their graph. All right, so let's go ahead and take a look at the warm-up first. So notice that there is a table given to you with a standard form and a factored form side. So go ahead, take a minute, pause the video, and complete each side of the table. And then I want you to think about question 2. Question 2 asks you, what do the quadratic expressions in each column have in common, besides the fact that everything on the left column is standard form and everything on the right is factor form. So go ahead and pause the video and do that now. All right, so let's go ahead and first take a look at our table. So when x squared is when that is considered standard form, the factored form of that would just be, let's do blue, x times x. When we have the factored form x times the sum of x and 9, the standard form would be x squared plus 9x. Okay, x squared minus 18x, the factored form would be x times x minus 18. For x times the difference of 6 and x, our standard form would be 6x minus x squared, or you could even write this as negative x squared plus 6x. For the next one, we have negative x squared plus 10x. There's a few different options that we have for here. You could have it as negative x times x minus 10. You could have it as x times negative x minus plus 10, sorry. So plus 10. Or you could even have it as x times 10 minus x. Okay, and then finally we have negative x times the sum of x and 2.75. So when we do that one, we end up with negative x squared minus 2.75x. Now, some things I want to point out for what do the quadratic expressions in each column have in common. So let's take a look at all the quadratic expressions in standard form first. And what do we notice that they have in common? Well, in every single one, there's a squared term and a linear term. There is no constant term. So let's jot that down. All expressions in standard form do not have a constant term. Okay. So if we ask ourselves from these expressions, what can we predict, if anything, about the features of the graph that represent them? So let's think about this. If there's no constant, that means the y-intercept is going to be 0, 0. So they all have the same y-intercept. Now, if we look at the factored form, what do we notice that they all have in common? Well, they are all in the form of x or negative x times a sum or difference. So now if we ask ourselves to make a prediction on the features of the graph based on this information, we can easily see what the x-intercepts are going to be, and then from that we can then see what the x-coordinate of the vertex will be. So can easily see x-intercept and x-coordinate of vertex. So remember, we have looked at how the constant term and the coefficient of the squared term affect the features of the graph representing a quadratic function in previous lessons. Now we're going to explore how the linear term influences the graph. So let's move on to the next activity. All right, for this next activity, you're going to need to use Desmos. What you're going to do is start by graphing the equation y equals x squared, and then experiment with adding different linear terms. So for example, try x squared plus 4x, x squared plus 20, x squared minus 50x, and then record your observations. Once you do that, you're going to repeat the process, but this time you're going to use y equals negative x squared and do the same thing. Experiment with adding different linear terms. After you've done that, go on to the next page, and without using graphing technology, fill out the table using the observations that you made from the first question. After you fill out the table, go ahead and also answer question number 3. So pause the video now and do that. All right, so some things that I noticed when I tried experimenting with different linear terms in the equation y equals x squared is that it still looked like a quadratic function. It's still a parabola, but what's happening is that it's shifting both horizontally and vertically. So adding a positive multiple of x to x squared, positive, a positive multiple of x results in it shifting down and to the left. Okay, but when I added a negative multiple, of x, it still shifts down, but this time it goes to the right. So it shifts down and to the right. Now with the negative x squared, y equals negative x squared, when I am adding a positive multiple of x, works the opposite of when you add it to y equals x squared. This time it shifts up and to the right, whereas adding a negative multiple of x, the graph shifts up and to the left. So when I start with a positive x squared, meaning it's more U-shaped, when I add a positive multiple of x, so I'm adding a positive linear term, my graph is going to shift down and then also to the left. When I add a negative multiple of x, so a negative linear term, it's going to shift down and to the right. For when my graphs are y equals negative x squared, meaning it's an upside down u, if I add a positive multiple of x, so a positive linear term, this time it's going to shift up and to the right. When I add a negative linear term, it's going to shift up and to the left. All right, so for the next question, it asked us to complete the table using our previous observations. So if you think about when we added a positive linear term to a quadratic term, our graph shifted down and to the left. So therefore, if my x-intercepts was 0, 0 when it was just x squared, my x-intercepts are now going to be 0, 0 and negative 6, 0. That explains the shift to the left. To figure out the x-coordinate, you're just taking halfway between the 0 and the negative 6, which in this case is negative 3. Okay, for the next one, this one is going to show a shift down and to the right. So my x-intercepts are 0, 0 and 10, 0. To find my x-coordinate of the vertex, just go halfway between 0 and 10, which is positive 5. All right, when I add a positive to a negative quadratic term, I am going to end up with a shift to the right. So that becomes 0, 0 and 50, 0. Again, for my x-coordinate, I just go halfway between 0 and 50, which is 25. Okay, for the last one, this one's going to be a shift to the left. So my x-intercepts are going to be 0, 0 and negative 36, 0, with my x-coordinate being negative 18. Now, if the shifting was a little tricky for you, you can also think of these as another way. You can think of these in their factored forms. So x squared plus x in its factored form is x times the sum of x and 6. For the next one, that would be x times the difference of x and 10. For the next one, you can think of these two as in negative x and x minus 50. And for this one, it would be negative x and x plus 36. All right, let's take a look at question 3, which asked us to look at equations with no linear terms, but there are constant terms, and it wants us to find the x-intercepts and the x-coordinate of the vertex of the graph representing each equation. One thing I do want to point out is that sometimes it is possible for the graphs to not intersect in the x-axis. So if you got stuck, hopefully you went ahead and used decimals to graph it. For A, in this case, the x-intercepts are going to be negative 5, 0 and 5, 0. And that makes the x-coordinate of the vertex to be 0, because halfway between negative 5 and 5 is 0. But for B, there are no x-intercepts. So no x and So no x-intercepts. The x-coordinate of the vertex is also 0 for this one. And that makes sense, right? If you have no linear term, there's no shifting side to side. So the x-coordinate is going to stay 0. So keep in mind that when there is no linear term but there is a constant term, it's not always easy to tell what the x-intercepts are going to be when the expression's in standard form. So, for example, in question A, there are an x-intercept. There are two x-intercepts, but in question B, there isn't. But we're going to continue to work on that and make sense of quadratic equations and that'll come up in the rest of this unit and in the next unit. All right, for this next activity, you're going to be using Desmos again to determine what the equation is for each of the graphs listed below. So when you are working on this, focus on what makes the 3 points up here. Okay, so think about your x-intercepts, if there's any, your y-intercepts, and your vertex. So go ahead, pause the video, and attempt those equations. Okay, so for graph A, we notice that both the x and y-intercept are 0, 0. There's no shifting going on. It's opening up, so therefore my equation is going to be y equals x squared. Okay, for B, a couple things that I've noticed is that it is a shift straight down. I notice that my x-intercepts are +3 and -3. So there's a couple of different ways I can look at this. If I take just the x-intercepts into mine, I could say my equation is x minus 3 times x plus 3. Okay, if I think about the shift in the graph, okay, I see that it's shifting down. There's no side-to-side movement, so that means my equation would just be x squared minus 9. Okay, for C, I see that my two x and y intercepts are -2 and 0. And then I also have a vertex of 0.5, -6.25. So I'm probably going to focus in on the x-intercepts, and I'm going to say that my equation is x plus 2 times x minus 3. For D, again, I notice that my x-intercepts are -0 and 0, so that means my equation is going to be x times x plus 6. All right, let's go ahead and look at E. Now, E is a little different than the other ones. I notice that I am opening down instead of opening up. So that means my x value, or my squared value, is going to be a negative. Now, since I know it went straight up without shifting side to side, I can just say that's -x squared plus 4. If I want to think about in terms of the x-intercepts, because I'm opening down, one of these are going to be the opposite. So my x-intercepts are -2 and +2. So to write the -2 one, I would say it's x plus 2. But to do the second one, because I have to take into consideration this negative sign right here, it now becomes -x plus 2 instead of just x minus 2. I'm applying that negative sign. I'm putting it back in. All right, let's take a look at graph F. Now this graph looks a little different than what we've seen before. Notice that there's only one x-intercept and the y-intercept is not at the origin. It is actually at 0, 4. Looking at the x-intercept of 2, 0, if we were to write this equation in factored form, we would say, well, one of them is definitely going to be x minus 2. Well, there's still 2 zeros in this case, and it's just another x minus 2. So this is one of those tricky situations where, although you only physically see one x-intercept, there's actually 2 occurring, and it's just a repeated form. So we call this actually a double root. So our equation for this graph would be y equals x minus 2 times x minus 2. All right, let's look at G. So again, G is upside down. I also noticed that it has a x-intercepts of -1 and 3. So when I write my equation in factored form, I have to take into consideration that one of them is going to have a negative x, and it's going to be the opposite of what we typically would write it. So if I have the positive 3, that would just be x minus 3. And the negative 1, typically we would write it as x plus 1, but because this is upside down, it becomes negative x minus 1. Now, I didn't mention this in the previous problem, and I should have. It doesn't matter which one you apply the negative to. So you could have actually applied it to the 3 and made it negative x plus 3 times x plus 1. So either one is fine. It just has to be applied somewhere. All right, let's look at h. So for h, we have 2x intercepts at positive 1 and positive 5. It opens up, so my equation would be y equals x minus 1 times x minus 5. All right, let's take a look at the last two. So graph I is a little bit different. There's no shifting side to side, doesn't move up or down. There's the x-intercept and the y-intercept are the same. Everything's at the origin. But what I do notice here is that these two ordered pairs are different than the very first graph we looked at, right? In the first graph, my ordered pairs were negative 1, 1, and 1, 1. But these are actually negative 1, 2, and 1, 2. So it's actually stretched a little bit thinner than my original graph. So by stretching it out, what's happening is you're multiplying the squared term by 2. So in this case, our equation is going to be y equals 2 times x squared. Okay, for my last equation, I noticed that the graph is upside down, so I know that it's definitely going to be a negative squared value. I also noticed that it has spread apart some, so it's kind of the opposite of what we were doing with this graph where it was stretched out and it was getting closer together. Now we're falling apart and it's getting wider. So when that happens, that means I am multiplying by a number between 0 and negative 1 in this case. So if my ordered pairs on here are negative 4, and 4, negative 4, that means that I have to be multiplying by a negative 0.25 times x squared. The reason why I know it's 0.25 squared, if I were to square my x value, which is going to be equal to 16, I have to ask myself what times 16 is going to give me negative 4. And in this case, it's going to be negative 0.25. So some takeaways from this activity, some things to take into consideration. When the graph opens up, our squared term is going to be positive, and when it opens down, our squared term is going to be negative. When the two x-intercepts are known, we can just write the equations in factored form. Okay, another thing to think about is that when the y-intercept is not at 0, 0, and the graph is centered on the y-axis, the equation in standard form will have the form of ax squared plus c. So there's no linear term, where 0 comma c would be the y-intercept. And finally, when 0, 0 is the only x-intercept and the y-intercept and the vertex, the equation in standard form has only the squared term ax squared. So there's no constant and there's no linear term in that case. So that is all for Unit 6, Lesson 13.